In this lecture of electrical fundamentals, we will cover DC source, voltage, current, resistance, Ohm's law, energy, power, and Watt's law. In addition to the topics that we'll introduce, we will do a series of problems, and hopefully that will help you understand better these concepts. As you know by now, in electrical engineering and in electronics, we focus a lot on the relationship between voltage, current, and resistance. And they all come together under the relationship of that is introduced by Ohm's law, which we will see soon. But before we get there, I think it's important to really understand the role of each of these different components. So this is a kind of a cartoonish picture that shows the relationship that we have. So we could think of volts as the pressure that is trying to flow of potential energy, and you have the amps, which is what actually flows into the into a conductor, and ohms or resistance is essentially any obstruction that you have in the medium where the current is flowing. So I mean, this is kind of a cartoonish picture, but it does convey a message of how the relationship between volts, amps, and so volts, currents, and resistance. So in a similar way, one could also look at the analogy with a water system. So you have you could think of this as a system in plumbing or as a water pipe that we have, and you perhaps have a water pump, and this is a pipeline. So it's a water pipeline. The pipeline could be made from different material, so it could be made from plastic or metal, doesn't really matter at this point. And you have the volume that flows, the rate of water that flows in the pipeline in terms of centimeter cube in this case. Basically it's a unit for volume. Yeah, so an amount of volume over a certain second. So every second you have certain volume that flows into the pipe, and as it goes through the pipe, once in a while you might find obstructions. So basically anything that will hinder the flow of water. So rocks, residue, dirt, anything that could obstruct the flow of water. In this example here, it's not really residue that causes resistance, but it's really the shape of the pipe itself. It becomes narrower, and that in a sense also models or it gives us some resistance to the flow of water. So this is a nice picture, and this is a good analogy with what actually happens with electrical circuits. So our water pump is essentially a battery. We have a battery, it's an energy source. This is where we get the energy to the circuit. You have your conductor, you have a conductor here. This is kind of the pipeline, if you will, for where current will flow in, whereas this is the pipeline where water will flow in, and you have current. Current essentially is your volume flow rate. So for us, current is really the amount of amps that goes into the wire. And if you will, I mean, from physics, we know amps is just basically the unit of charge over seconds, or coulomb per second. Whereas here is cubic volume per second. And as it goes in, you have certain resistance, whether the resistance of a material, if you use a specific material, that adds certain resistance, or it could be the resistance that you have, so an actual resistive device. And we talked about resistors in lecture 2. And then the loop is closed. So in both of these analogies, you have a closed loop where there is a flow. The flow continues. There's resistance, but there is nonetheless flow of the water. In here, there's a flow of water. There's some resistance, but it flows. And in here, the same thing. There is resistance, but the current still flows. So one thing you should realize between current, voltage, and resistance is that current goes through the resistor. Voltage is across the resistor. So voltage is always across a resistor, and current is through the resistor. And that's why in the lab, if you were to measure the voltage across a resistor, what you do is you basically put your leads or your alligator clip on this side and on this side. So you connect them one here, and then that gives you the voltage across the resistor, or your probes basically. And if you want to measure the current through the resistor, you have to break the circuit. You have to break the circuit, literally cut it, and you connect this. When you make an opening, you let the current flow in through your DMM, through your digital multimeter, and that's how you measure current. So current is always through, and voltage is always across, and that's kind of what we wanted to show you here. I think most people are familiar with Einstein's famous equation from the special theory of relativity, E equals to mc squared. And it's an incredible formula. It's very popular. It has a lot of implications, and it gained quite a lot of popularity, as it should. And for us, as similar to E equal mc squared, for us the equation that is extremely important for electrical engineers is this equation: V is equal to Ri. And for both of them, whether E equal mc squared or V equals to Ri, what makes it so interesting is that it has so many different implications in real life, and in addition to that, it is an extremely simple and basic equation. In fact, if you look at this equation, it's ridiculously simple. There's just it's very linear to each other. It's just voltage equals to resistance times current. So all electrical circuits that exist in life, they essentially function based on this. They always operate based on this. It was discovered in 1827 by George Simon Ohm, a German physicist, and until today, this is the basic law that we use in electrical engineering. So as I wrote to you here, it is the most important fundamental law in electronics. Undoubtedly, there's no other that can come close to it. So I hope you all will remember this. It's very basic, and probably you all know this equation by now. Maybe we could test this equation just to see how we could put some numbers to better understand what's going on. So let's maybe look at this question. What is the current in a circuit with a 12-volt source? So we know that V is 12 volts if the resistance is 10 ohm. So we have V is 12 volt, we have the resistance is 10 ohm, and we want to find the current. So what you would do in this case is you essentially need to isolate for I in here. So I would equal to the voltage divided by the resistance, and the voltage is 12. We divide it by 10, and that should give us 1.2 amps. 1.2 amps, and this is what we get. In fact, if you notice here, I wrote 1.20 amp. Why do we put a 0? Because we said in this course we want to always use 3 significant digits, and that's why there's a 0 here. So I hope that you don't forget that in an evaluation. And of course, don't forget the units. The units is very important. This is a measure of current, so we should not forget to include the A for current. In reality, you will, in this course, you will probably see current either in amps or in milliamps. These are the two traditional units that you'll end up seeing. One is just the engineering prefix of the other. Let's do another question. So here, question number 2, what is the voltage? So we're looking for V, this is the unknown, across a 600 ohm resistor if the current is 26.5 milliamp. So we have the resistance, which is 680 ohm. We have the current, it is 26.5 milliamp. Be careful, this is a milli, so milli is essentially times 10 to the minus 3, and we need to find the voltage. So for the voltage, what we do is essentially we multiply these two together. But when you multiply, you need to put them all with the same prefix and the same kind of similar unit. So if it's milli, you have to change it to 26.5 times 10 to the minus 3 times 680, and this should give you the result of that we get for voltage. Or else what you could do to get rid of a milli is to change this into a kilo. So you could say 0.680 kilo ohm times 26.5 milliamp. That should also work, because a kilo is times 10 to the 3, and milli is times 10 to the minus 3. When you multiply them together, times 10 to the 3 times 10 to the 3 times 10 to the minus 3, that becomes a 1. So when you multiply them, you should essentially get a value of 18. Now, if we just put it with 3 significant digits, we'll get 18.0. I put an average here because there's other digits as well, but we'll just drop the others because we want to get as precisely 3 significant digits. So if we do 0.68 times 26.5, that gives us 18.02, and the 2 is dropped because we want 3 significant digits. This is another question that we could work on related to Ohm's law. So in question 3, we can read it. What is the resistance of the light bulb? Now, the light bulb is an electrical component, so it's not a resistor. But in reality, any component, any electrical component, will introduce some resistance to it, and some resistance to the circuit. So one way to measure the resistance of this would be, for instance, to take the ratio of voltage and current, and through that we could in fact determine how much resistance does this electric component introduces to a circuit. But otherwise, as is, if you look at it, it's a light bulb. It's a device that gives us light. So how do we do that? Again, we want to figure out the voltage and the current through the light bulb and the voltage across the light bulb. So in this setup, what we have is we have an energy source of 115 volts DC that goes into a DMM, a digital multimeter, and from the DMM it goes to the light bulb, and the loop is closed. So if you look at the current flows like this. It goes through the DMM, it comes out of the DMM, it enters the light bulb, it goes through this wire, it goes back to the energy source, and again, this is the entire loop. So the loop is closed, and we expect to see something. And in fact, you see the effect of the closed loop because you in fact see a light. You see the rays of it, and the light is lit on. And so that kind of gives you a hint that it is functional. But maybe I should also mention that this picture is also not 100% accurate. A light bulb or any electrical equipment, cell phone, laptop, anything, you need to have a direct current to make it functional. You cannot just connect it straight to an alternating current because this is the wall, right? This is the electric outlet that you have on the wall. This gives you an AC, an alternating current. So you can't just connect a light bulb to an alternating current. You need to change it to DC. And then you could do that. So usually what you need is a device, right? A device that is called an AC adapter, like you have with your cell phone when you charge your cell phone, or like you have with your laptop machine when you charge your laptop machine. You have an AC adapter. So the AC adapter, what it does is that it's connected to the wall. It takes an alternating current, and then the AC adapter changes the alternating current to a DC, to a direct current, and this is what is fed to your device. Okay, so if you were to try this setup at home, don't put it like this. You need to certainly to have some AC to DC adapter, some adapter that will do that. Here, where does this value comes from? Well, I mean, this is something that so you could think about it as an RMS, as a root mean square value. So root mean square value is anytime because this is an alternating current, right? So an alternating current is essentially maybe I could explain it very briefly. So you have time and you have voltage, and it just alternates. It's a sinusoidal, and it alternates, and it has a certain peak voltage, so V peak, and it has a certain period, and by knowing the period and knowing the peak voltage, you could in fact average this. You could average this this signal, this sinusoidal electrical signal, and you could say, well, instead of having an alternating current, what if this thing was a DC source? What would it be? And this is why we use something called the RMS. So if we check the RMS value of this, of like what we have here in North America, typically we expect an RMS, what you get from the wall, an RMS of 120 volts. What this means is that you take the peak voltage of North American electric outlets are 170 volts, 170 divided by square root of 2. And that's what gives you a roughly a voltage of 120 volts RMS. So when we say 120 volts, or in this case it's mentioned 115, it's more or less the same. This is really an RMS value. So this is kind of a saying that if this alternating current was a DC power, what would this voltage be? This is what this means. So again, if you do the setup, be careful. This would not work at home. You all absolutely need an AC to DC converter to make such a device function. So let's continue. So let's just assume it's just a battery. We have a battery of 115 volts. So this is the voltage that we have. So this is the voltage. And because there's nothing else connected here, we assume that this has negligible resistance, this DMM. This is a DMM, digital multimeter. It has negligible resistance. Then the entire voltage is really dropped here. So this entire 115 volts is really what you get here. There's a plus, there's a minus. This is really what you get here. You will get 115 volts across this light bulb. And as for the current, well, the current, you could see it here. You could see it in the DMM. The current that flows in the wire, the current that flows inside the wire is 0.87 amps. 0.87 amps, and this is what the DMM tells you. Is the DMM connected properly? It is, right? So this dial is placed on A for amplitude. The plus is connected to A. So when we want a certain range that is not in the milliamps, but it is in the amps, it's connected here. So this is good. And the negative is connected to the common. To the common, it's here. And your current goes through the DMM into the light bulb and all the way there, right? So now you have a closed loop. It comes here, it goes into the DMM, it leaves the DMM, it enters the light bulb, and it leaves the light bulb, and all the way to a closed circuit, all the way to a closed circuit. So there's an absolute closed circuit here, and you see the effect of it by having this light bulb. So now the question is, what is the resistance of the light bulb? So the resistance of the light bulb, again, we go through Ohm's law. So V is equal to Ri. V is equal to Ri. Or we could say that the resistance R is equal to the voltage divided by current. Right? Voltage divided by current. So the voltage across the light bulb is 115 volts. And the current is 0.87. 0.87. amps. Okay, so you take the ratio, this ratio, so you do 115 divided by 0.87, and essentially what you expect to get is essentially 132 ohms, and we put roughly because we bring it down to 3 significant digits. So although this is just a light bulb, but it has a resistance of 132 ohms. Okay. We can also see Ohm's law graphically, and I think this also gives us some interesting insight into how Ohm's law functions. So if we go back to the basic definition of Ohm's law, which is V is equal to Ri, but now we readjust it and we solve for I. We solve for the current. So we can simply write it as current equals to voltage divided by resistance. And now we could see two different ways of looking at this equation, this Ohm's law equation. One way would be to essentially look at the relationship between current and voltage while keeping R fixed at a certain value. Another way would be to look at the relationship between current and resistance while keeping the voltage fixed at a certain value. So what this leads us to say is that current and voltage, the relationship between them is proportional. This is a symbol for proportionality, and they are in fact directly proportional. If this one goes up, this one goes up. If this one goes down, this one will also go down. As for the relationship between current and resistance, it is inversely proportional. So if you increase the current, this will lead into a diminution or the decrease in resistance. And vice versa, right? So they are inversely proportional. They're not directly proportional like this one here. So if we were to plot it for different results here, so let's say we consider some fixed resistance and we plot a current versus a voltage. This is what you get. You will get a straight line. And the straight line will always pass through zero, always pass through this zero. And this is essentially what we get. If we do it for the other one, for the relationship between current and resistance. So we look at the current for different resistances while keeping the voltage fixed, we get a hyperbola. So maybe you've seen this in math. This is basically the equation for y equals to 1 over x. It comes down, it goes down, but it goes down not in a sharp way, it goes down in a smooth like this. So it's not sharp, it's not a line, it's a hyperbola. And that's the result that we get. Now, what is interesting here for the linear one, for the current and voltage relationship, is that you can find the slope. This line, that's a line, right? And every line will have a slope, so we can certainly find the slope. And to find the slope, we need 2 points. So let's consider this pair, V1 I1 and V2 I2. So this is V. So V1 in this case would be 5, and I1 would be 2 milliamp. And V2 would be 20 volts, and I2 would be perhaps, I can't see very well, but perhaps 7.5 milliamp. So you have 2 points, and through we know from math that the slope is simply rise over run, or delta y over delta x. Delta y would be delta current over delta voltage, right? And this will help us to figure out the slope. So if we find the slope, we just do the equation for slope from math. We determine the slope here, and this slope, what is interesting is that it is equal to G. And G, we talked about it before. G is simply the conductance. And if we know the conductance, right away we can determine the resistance. It's just 1 over. So anytime you have a current versus voltage plot, if you find its slope, the resistance will be 1 over that. So it would be resistance is equal to 1 over the slope of an I versus V plot. Now, notice that, as we said before, 0, 0 is always one of the points on the plot. So instead of putting one of the points anywhere, we could in fact choose 0, 0 as the second point. It would make our analysis much easier. So let's just remove it from here, and let's just put it here. And if you put 0, for I1 and 0 for V1, your equation for the slopes simplifies to simply this. Now, what this leads you to say is that in order to find the slope for Ohm's law in a current versus voltage, you simply need to find 1 point on the line, and that's it. You take the ratio of it. You divide the current by the voltage, and this gives you the slope. This gives you the slope. And now that you have the slope, you do 1 over that, and that gives you the resistance. Now, maybe this is all overwhelming with a lot of equations and explanation, but maybe we'll see a few examples, and this should essentially help us better understand what's going on. So let's look at the question 4. What is the conductance and resistance of this plot? So we give you a plot. First thing first, when you look at a plot, is you simply look at it very quickly. It's a line, and it's a positive slope. So you know certainly this is related to the relationship here, current versus voltage. In fact, you can see it. It's current in milliamps versus voltage. So we expect a line, and that's perfectly correct. If it wasn't a line, if it was a hyperbola, it would be current versus resistance, but not current versus voltage. So now that we have this, we want to find what is, from this plot, we want to determine what is the resistance, or what is the conductance, right? And the relationship between these two is just 1 over the other, right? So conductance is equal to 1 over resistance, or if you will, resistance is equal to 1 over conductance. Conductance has a symbol G, and resistance has a symbol R. So so as we said, you just need 1 point on the line, and that will give you everything. So you can pick whatever point you want. Don't pick 0, 0. If you pick 0, 0, that's not going to work. It's going to be 0 divided by 0. That's an indefinite form, like we saw, or like you saw in calculus. So you cannot pick 0, 0. It has to be anything but 0, 0. So maybe one number that we could pick is this one here. This one here. So we could simply pick this one here. and this is 27. So if you look at the voltage, it's 27 volts. And in terms of the current, is 10 milliamp. So what we do is we say the slope is equal to 10 milliamp over 27 volts. The slope is equal to 10 milliamp over 27 volts. And we know this will give us G, the conductance. And the result that you get is 0.370 milliseconds, 0.370 milliseconds. Now you might say, where did the milli come from? It came from here, because this shows in milli, and therefore you have to bring it here. You have to put milli in here, and this is millisiemens. So this is a conductance. So we basically answered this question. What is conductance of this circuit? Well, from the graph we determined the slope, and the slope gave us the conductance. Now, what about the resistance? It's just 1 over that, and because you do 1 over 0.37 milli, anytime you have a milli in the bottom, on top it becomes a kilo. And that's why we end up getting 2.70 kilo ohm, right? So maybe I could explain this a bit more. So if you, let's say you have 1 over some number with a milli, it will equal some number with a kilo. It has to, because this is basically 1 over 10 to the, minus 3, which essentially is simply equal to 10 to the 3, right? 10 to the 3 is kilo, and 10 to the minus 3 is milli. And this is 10 to the 3 is this thing here. 10 to the 3 is kilo. Okay, so I hope this kind of helps you make better sense of all these equations through this example. We'll do another one on the next slide. Question 5, what is the conductance and resistance of this plot? And so we have a plot, and we need to find the resistance and the conductance. So R and G. So again, just to recap, we have a current in milliamps versus voltage. And as you notice, it is a straight line. How did we get this straight line? Well, what we basically did is we got points in the lab. So basically we had a circuit, and we have a power supply, and we have a DMM that is connected to the circuit. So as we move the values of the power supply to 2 volts, to 4 volts, to 6 volts, to 8 volts, to 10 volts, we got different readings on the DMM for the current. So we got this current here, we put a dot. We got at 4 volts this current, we put a dot. At 6 volts we got this current, we put a dot. At 8 volts we got this current, we put a dot, and so on. And then we use regression or curve fitting, or not even all that. We simply place the straight line between the dots, and this straight line tells us the relationship between current and voltage. So this was obtained, the dots are obtained experimentally, and the line is what we do after the experimental result that we got. So now, how do we find the conductance and resistance? We simply need to find the slope. So for the slope, we said we just need 1 point on the line that will give us that. I think one good point that we could pick is perhaps this one here. Perhaps this one here. So at 8 volts, we have 13 milliamp. And so we could simply find the slope as G is equal to 13 milliamp divided by 8 volts. And you get 1.63 millisiemens. And again, the milli comes because this is milli. Now we do the 1 over of the result, 1 over G, and that gives us 614 ohms. Right? So you might get 0.614 kilo ohm because you have a milli in the bottom, but then you write it in engineering notation, and then you'll end up with 614 ohms. Question 6, if resistance is varied, so we will vary this time the resistance. Resistance is what changes. For a constant voltage of 3 volts DC, plot the IR curve. IR, which is the current, versus resistance. Right? So if we recall from what we saw earlier, when, again, we go through Ohm's law, V is equal to Ri, or we could simply say that I is equal to voltage versus resistance. The relationship between this one, current and resistance, is inversely proportional. Right? So this is resistance and this is current. It is inversely proportional. It's something like this, right? And this is true for a specific V. A V equals to constant. In this case, it's equal to 3 volts. It's a specific voltage, specific V. So it's a V naught, it's fixed. So now this is kind of what we expect here, right? So if we do it, we get the following results. Right? So we get different points, and we end up, building, getting it for different results, and then we put the line through the result. We'll end up getting such a thing as we expected. Now, what one could also do is to figure out some of the characteristics that we want here. So, for example, if we look precisely at, for instance, this is 1 kilo ohm, this is 0.5 kilo ohm, and this would be 0.3 kilo ohm, or if you will, 300 ohms. So at 300 ohms, we get a current of 10 milliamp. Okay, and here we have another point that we could also get, because these are points on the plot. At 3 kilo ohm, we get, I guess, 1 milliamp. So at 3 kilo ohm, we get 1 milliamp. And again, both of them should work with Ohm's law. So we could, I guess, try it. We could try it. Maybe I could just write it here. So this is 300 ohms. 300 ohms. And this one here is 3 kilo ohm. And this point here is 10 milliamp. And this one here is 1 milliamp. 1 milliamp. So if we do the multiplication of 3 by 1, 3 kilo ohm times 1 milliohm, 3 kilo ohm times 1 milliamp, this should give us basically 3 volts, and this is what we expected. And if we multiply 300 by 10, or if you will, 0.3 kilo ohm by 10 milli, then this should also give us 3. So they're both correct. So this is only true for a fixed value, fixed. And this is why it's important. Now, if we change the value, and I mentioned this before, if we change it, instead of 3 volts, we get some other, let's say 5 volts or 6 volts, the plot will be in here, right? It will be more on this side. So the more you go farther away from this one is because the voltage is being increased. If the voltage is decreasing from 3 volts, you will have plots that are here and that are getting closer to the origin, right? It won't touch it, but it will get close to the origin. In lecture 2, we saw breadboards, and in this question, we will have a breadboard in it. So let's read the question now. If the resistor is green, blue, brown, and gold, what should the ammeter read? So this is the ammeter. This is the ammeter. If you will, I could show you an actual picture of an ammeter. This is how an ammeter looks. Essentially, it's just by looking at it, you have a needle and you have a measurement that you could do, and you connect it between these two, the black and the red, and this allows you to measure the current through a circuit. But to be honest, nobody really uses an ammeter today. This is very dated. It doesn't give you proper reading. It's not very accurate. There's human perception involved in here. You have to have good eyes to see where the needle hits. It's very analog, so it's not really used. So in fact, you could do the same setup, and instead of an ammeter, a better option would be to have a DMM, a digital multimeter. But just nonetheless, it's here in the problem, so why not know what historically is a DC ammeter? So basically, it's just a device that measures current. So let's look at what we have in the setup. We have our energy source, which is the power supply. So it's a power supply. The power supply has 2 channels. This is one channel. This is another channel. This is your minus. This is your plus. And it's always good to stick to the convention of putting red to the plus and black to the minus. Black wires, black leads, or probes. And so now, and you also have your breadboard. So you are feeding your breadboard on this side, on this line, which we said is all connected together with the positive, on this side with the negative. And from here, you could pick it from anywhere. It's the same node, right? They're all connected together. So we pick it from here. and we connect it to the positive of the, if you will, the DMM or the DC ammeter. And from the negative of the DC ammeter or the DMM, we bring it to one of the locations of the breadboard. So this is a new location. We haven't used this node before. And then from the same row, they're all connected together. So this is one node. We connect a resistor, and the resistor is connected to a different location. From this location, we pick a jumper or a wire, and we go all the way to the negative line, and then this is all connected together from the negative line back to the power supply. So if you look, there is a 100% a closed loop. 100% closed loop. This, the current moves like this, like this, through here. It leaves the ammeter. This is all connected together. This is connected together, so it passes through the resistor. It comes through the wire. This is all connected together from the inside of the breadboard and back to the power supply. So that you certainly have your closed loop, and your power supply is turned on. You've set it to a specific voltage. You set it to a specific voltage, a 15 volt on your power supply. So you have your VDC, your DC at 15 volts. 15 volts. You have your ammeter, the device, or if you will, we could also think of this as your DMM. And we want to figure out what should this read? What should the current be? Here, what is this equal to? So through Ohm's law, we know that we need to have two of the three variables. So we have Ohm's law, which tells us V, maybe I could write it here, V is equal to Ri, or if you want I, because we want to find the current, is equal to the voltage divided by the resistance. Voltage we know, voltage is 15, resistance we don't know, but we're told the color code, right? We have the color code. It's green, blue, brown, and gold. Green, blue, brown, and gold, right? So let me just bring the highlighter here, the pointer. So green, blue, brown, and gold. Now, in case you forgot, I'm going to just bring the table from what we saw before, and let's just make sure we have this. So green, so you come in for band 1 for green. Green is here. This is your green for band 1. Blue, band 2, blue. Blue is here. And brown for band 3. Brown, so this is here. And then gold for band 4. This is here. So we could certainly write it. We could write it. So 5. Blue is 6. So now we're kind of merging both skills from lecture 2 and skills of today's lecture. Brown is times 10 to the 1. And your the tolerance is plus or minus 5%. Plus or minus 5%. Okay, so this is 56 times 10, which basically you could say that the nominal value is 560 ohms. 560 ohms. This is your resistance. We could relax and ignore the tolerance for now. We could just take the nominal value and ignore the tolerance. We could just do that. And so in here we could just simply put 560. 15 divided by 560, and let's see what this gives us. 15 divided by 560, or if you want to put it in engineering notation, it will be 0.56 kilo ohm, which means anything over a kilo becomes a milli, so it's 26.8 milliamps. And that's what we expect to see in here with the DMM or with this DC ammeter, with this kind of device. Okay. In this lecture, we also wanted to discuss some of the topics related to energy and power. I'm almost positive you've seen this in other places, including in physics courses, but here we want to kind of show you how energy and power also is critical when we discuss electrical circuits. So the relationship between energy and power is really defined by this equation. So this is power, big P, in the for power is measured in watts. It's equal to energy. Energy is measured in joules, and these are, by the way, the SI units. And T, time, is measured in seconds. So again, based on the International System of Units, we have to use joules and seconds. So this is the relationship between both of them. Sometimes people confuse the relationship between both. Sometimes people, when they talk, they use them interchangeably. They're not the same. It's like saying distance and speed. Distance is something and speed is something else, right? So if I say the distance from Toronto to Montreal is 500 kilometers, this is one piece of information. And if I say one would go from Toronto to Montreal at the speed of 100 kilometers an hour, that's a different piece of information. They're not the same. They're related to each other. So if you know the distance and you know the time that it takes, you can find the speed, but they're not the same. So this is the same thing here with energy and power. P is a rate. So you could think of P as in terms of distance, it would be kind of a speed. Your 100 kilometers an hour. And E is a quantity, so like the distance, the separation. So one has to be a bit careful here. Now the formal definition that we give you, these are like brief, very short definitions. So power is the rate of doing work. So that's that. Sometimes it's a bit hard to understand what this means, but I hope the explanation that I gave you conveys the message. Now, in terms of units, watts is something that we will use anytime we discuss power. And in reality, watt is made up of the ratio of joules, which is the quantity for energy, divided by seconds. So if you have any measure of joules by second, that gives you your watts, right? So that's something that is also useful to know. I have this picture that I wanted to show you, that basically energy is a quantity. So if you take a piece of chocolate, I mean, this is a chocolate bar. It's about 50 grams, and the quantity of energy that this chocolate bar has is about 900 kilojoule. That's just an example. There's nothing related to power with a piece of chocolate. It's a finite quantity. So hopefully, anytime you think of energy and power, you realize that anything that gives you or anything that has energy is a finite quantity, whereas power is a ratio. So that I hope that kind of sinks in. Sometimes it's a bit difficult. It will take some thinking to really wrap your head around this. But I think the analogy between distance and speed could be useful in this regard. Okay, so one other thing that I'd like to discuss is energy measured in kilowatt hour. Now, this is interesting for electrical engineers. In fact, anytime you get your utility bill, so the bill that you get of how much electricity you use at your home, at your apartment, at your place, that is sent to you by the electric power company within your region, whether it's Electra if you're in Mississauga, or if it's Hydro 1 if you're in different parts of Ontario, or if you're in Quebec, it will be with Hydro-Québec or Hydro-Québec. You get a bill. You get this bill that is sent to you, and in it you will always see how much you consumed, not power. Power is a rate, but how much you consumed of energy. It's a finite. It's like a piece of chocolate. It's a finite amount of energy that you consumed at home. When you turned on your electricity, you consumed a certain finite amount of energy. So it's not power. So I hope that's clear. So if you see kilowatt hour, that's what it stands for. K for kilo, W for watt, and H for hour. Sometimes it's written HR, but the scientific way of writing it using the SI notation, and in fact the conventions, is just to use H, kilowatt hour. This is not a unit for power. Although the W here, the watt, will kind of mess you up and make you believe that we're talking about watt. But anytime you see kWh, this is always a measure of energy. So always be mindful of this. So sometimes we will tell you how much you consume of energy in terms of joules, but sometimes we will talk about kilowatt hour. So when do we talk about one or the other? They're both the same. They're both energy. So usually we talk about joules when we are talking about a small amount. So if we say, for example, a piece of silicon chip that consumes this amount of joules, this amount of energy. It's very small. It's a tiny value. We usually use joules to refer to energy, which is basically the SI unit for energy. But if we are talking about a large amount of energy, we will not talk of joules. We will talk of kilowatt hour. Kilowatt hour is a unit of energy used by utility companies. Electra, Hydro One, Hydro-Quebec. It is also convenient for electrical appliances. So for sometimes you might see different equipments that you get, and then the amount of energy that a device might consume will be provided to you. In general, power is provided, but sometimes you'll find this as well. Okay, so remark, kilowatt hour is a unit of energy, not power. I hope this kind of, you will be reminded of this. Okay, so we said that energy sometimes can show up in kilowatt hour, especially when we're talking of big quantities, energy that you consume in a month, energy that you consume at home, and sometimes you will see energy in joules for something that is very tiny, like a small silicon chip that you have inside your computer. That's a very tiny amount of energy that you're consuming. It will probably show up in specification in joules. So here, let's see the question 8. How many joules are there in 1 kilowatt hour? Basically, we want to know that since both of them are energy, joule is in quantity for energy, kilowatt hour is a quantity for energy. But the question is, within 1 kilowatt hour, how many joules do you have? So let's see how to break this up. So we know from the relationship between energy and power is that power is equal to energy divided by time. And we're interested by this quantity or this quantity. They're both pieces of measures for energy. So we could isolate for energy, bring the time above. So we have energy equals to power times time. Energy is 1 kilowatt hour. The power that we consume, we could just break it apart in 2 parts. So this is 1 kilowatt. So we could just write 1 kilowatt. So 1,000 watt every 1 hour. That's what it means. 1 kilowatt hour is 1,000 watt every 1 hour. Right? So 1 kilowatt times 1 hour. And because we are using joules, joules is always used with SI units, so International System of Units. So we cannot work with hour. Watt we can work with, but hour we cannot. It has to be in seconds. Within 1 hour, you have 60 minutes. Within every minute, you have 60 seconds. So you would multiply 60 times 60, and that becomes 3,600. And then what we have is this amount times 1,000 watts. We multiply them together, and we end up converging to 3.6 times 10 to the 6 joules. So this is what we found out, is that within 1 kilowatt hour, there are 3.6 times 10 to the 6 joules. So you can imagine that utility companies will not use joules, because otherwise the number will be ridiculously large, and it's not very easy for your normal people, normal citizens looking at their bill with joules. So that's not very convenient to show, and therefore they use the one like this in kilowatt hour. Okay. Okay, let's move on to the next question. Question 9, what is the energy used in operating a 1,200 watt electrical heater for 20 minutes? So we have a heater, this heater here. This is connected to the electric plug, so it's plugged to the wall to get its to be sourced, to get its energy. And we are operating this, and we know that this device, if you look at the tag behind it, this heater, it will tell you that it consumes 1,200 watts, 1,200 watts. So if you turn on this heater for 20 minutes, how much energy would you be consuming? So let's go through the motions here. So energy is equal to power times time. Right? I mean, again, we took the power equals to energy divided by time. We rearranged it, so it's in this format. The power is 1,200 watts. The time is 20 minutes, so times 20 minutes. Because we want to have the measure in kilowatt hour, what we would do is we change the 20 minutes to hour. So 20 minutes is essentially 1/3 of an hour, or 0.333 of an hour. Right, so this 20 minutes is equal to this. Now if I multiply them through, so basically I do 1.2 divided by 3, I end up with 0.4. kilowatt hour, kWh, right? And this is what we get. So the amount of energy that this heater will consume is 0.4 kilowatt hour. Okay, so that shows you how we work with all these different equations. In this lecture, we saw Ohm's law as a critical, important law to use and to remember when we talk of electrical circuit. In addition to that, we also want you to learn and to acquire and to remember Watt's law. Watt's law can be essentially boiled down by simply this equation here. So power is equal to voltage times current. The other varieties of writing Watt's law are basically a derivative of this one. So essentially, if you merge Ohm's law with this, you'll be able to derive this, P is equal to RI squared, or this one here, which is voltage squared divided by R. So I think it's not a bad idea to know all three, but if you don't want to remember the others, this should be sufficient. They're useful in the sense that depending on what you have available at your disposal, if let's say you only have voltage and resistance and you want to find power, well, you have no choice but to use this one here. If you have current and resistance, you could use this. And if you have current and voltage, you could use this. So in an evaluation, and when we ask you for power and you need to converge to an answer quickly, this could give you a very nice shortcut. Instead of using Ohm's law to figure out what is missing and plugging it in this one, but I'll leave it to your discretion to use whichever you want. But in reality, if you were to only memorize one, I mean, this could be the easiest one to memorize. Now, in terms of Watt's law, I think it's interesting to highlight that power, as we said before, it uses the units of watt. Now, watt comes from, it's a name of a person. So it's this guy here. His name is James Watt. So he is a Scottish inventor. In fact, he was a mechanical engineer that existed from 1736 to 1819. And the unit for power was not discovered by him. It was in fact discovered by Siemens. He proposed these equations. It was him. It wasn't James Watt. Siemens was his full name is William Siemens. He was a German-British electrical engineer, and in 1882 he proposed this equation, and he said that he favors to have the power be in units of watt. So that's kind of interesting that 60 years after this guy is dead, his name is attached to an equation that he didn't discover. So that's kind of neat to know historically. So let's move on. So I also wanted to show you this thing here. You might see it in different places, perhaps in books and on websites and other places. This is known as Ohm's law formula wheel. It's very interesting. Sometimes it's provided to you with different kits that you buy from electronic stores. And basically the way it works is that it's kind of it's a guide to help you figure out whatever you're missing. So let's say you want to find resistance, right? So you go to R. And what you have at your disposal, let's say, is only power and voltage. Well, you could find resistance by simply doing this. You take the square of the voltage, you divide by the power, that gives you resistance. So in a sense, depending on what you're looking for, whether it's power, voltage, resistance, or current, it gives you different ways of converging to this answer. And you could use whichever variable or values you have for, and that's why it could be useful. But deriving this is pretty straightforward. You could derive this entire table simply by Ohm's law in this one here, and then you could derive this entire table. So deriving it is not complicated, but here I'm providing it to you so that in case you don't want to derive it every single time, you can simply use it and then see whatever you want. You want power and you only have resistance and current, well, you simply use this. You want you want current and you only have power and resistance, you could use this. To converge to current, and so it becomes very practical to find the answer fairly quickly. In an exam, this will not be provided to you, so you still have to kind of use your concepts of Ohm's law and Watt's law. So these are two things that you need to put in your toolkit, and I hope you won't forget. Memorizing the other two could be useful, so it's not a bad idea to do it as well, but otherwise I think you will be able to survive. Okay, so let's do this question. Question 10, what power is dissipated by a heater that draws 12 amps of current from a 120 volts DC supply? So we want to find the power dissipated by a heater, and we know the amount of current that it uses. So we have I is equal to 12 amps, and we know the power. So we have I, the current, and we have the voltage. So if I look here between the three, this one would work, right? I know the current is 12 amps. I know the voltage is 120, so I simply multiply them together, and that should give me my answer in power. So let's just do it. Let's just do it. So P is equal to VI, 120 times 12, that equals to 1,440 watts. We represent it in engineering notation, and we write 1.44 kilowatt. So that's the answer, 1.44 kilowatt. Okay, this is another question. Question 11. What power is dissipated by a 27 ohm resistor if the current is this much? So again, we're looking for a power for an electrical circuit. We know the current, we know the resistance, but we have no idea what power is. And let's say we didn't remember the equation that are shown there. We only remember that V is equal to Ri, so that's Ohm's law. You remember this one. And we also remember that P is equal to VI. P is equal to VI. V times I. Okay, so let's see what we have. We have the current. We have the current, so we have this one. So that's good. We have this one. That's good. We have the resistance. So we have this one. This is good. But we have no idea what voltage is. Right? So they basically just use Ohm's law, get this, and then plug it in here. Plug it in here. Right? So plug it in here. And if we do that, what you will end up getting, it would be RI squared. And now we have everything. We have the resistance, which is 27 ohms, and we have the current, which is 0.134 amps. But if you would have remembered the equation that I showed you before on the previous slide, which are the three varieties of writing power, which is power is equal to VI, voltage times current, power is equal to V squared R, and power is equal to RI squared, then you could have right away moved to this quickly. So this could be a very, I mean, it could be a shortcut during an exam. Instead of doing all this, right away you get here. So that kind of shows you the incentive for why memorizing the different varieties of Watt's law could be useful. So anyways, let's just do it. Let's say we know it in this case. P is equal to R times I squared. The resistance is 27, the current is this, we multiply through, we get 0.492 watts. We represent it in engineering notation, we move by 3 digits to the right, it becomes 492 milliwatt, and now we could simply write the answer. This is it, 492 milliwatt. Let's do another question. Question 12. So what power is dissipated by a 100 ohm resistor with a 5 volt across it? So again, let's say this time we also know the equations. So power is equal to V squared R. We know the voltage, it's 5. We know the resistance is 100, so 5 squared divided by 100. We get 0.25 watts. We can represent this in engineering notation. So we move to the right by 3 digits. It becomes 250 milliwatt. And this is the answer that we got. These are some key terminologies and definitions. We talked about them throughout the lecture, but if anyone is interested, you could pause the video and read it. And it continues for energy and power on the slide. These are some exercises that we can do together to better understand what is going on here. So let's read. Holding the voltage constant and plotting the current against the resistance as the resistance is varied will form which one? So just to recap from the lecture, we saw that if you have a relationship like this, where you have the current versus the resistance, you will have such a thing. We also saw that if you have the current, right, versus the voltage, you will have a straight line. So let's go through this. If you do this, and by the way, this is fixed for a fixed voltage. So it's a fixed voltage, and this is for a fixed resistance. Some fixed resistance R naught, some fixed resistance V naught. So will you have a straight line with a positive slope? This is wrong. Will you have a straight line with a negative slope? This is wrong. Will you have a parabola? A parabola is like this. This is a parabola. This is not what we got. This is different. This is a hyperbola. A hyperbola is something like this. Like this is the positive one. So this means that this is wrong, and the answer should be D. Let's see if that's the answer. The answer is indeed D. Question 2, when the current is plotted against the voltage for a fixed resistor, which one is correct? So again, what we're asked is this. We have the current against the voltage for a specific resistor, and it will be like this. This will be true for a specific fixed resistor. The slope will be G, the conductance, and you do 1 over that to get the resistance. So let's go through the options. You will get a straight line with a positive slope. That's correct. You will get a straight line with a negative slope. This is wrong. You will get a parabola. This is wrong. So a parabola is something like this. It's like a U shape. So this is wrong. You will get a hyperbola. So it's the 1 over x representation. So this is also wrong. So the answer is really A. Next question for constant voltage in a circuit, doubling the resistance means what? So you maybe we could just write it. So we could write the equation. So Ohm's law, V is equal to Ri. If we double the resistance, so this suddenly becomes 2R. So it becomes 2R. Doubling the resistance means what? Doubling the current? Well, we know the relationship between current is proportional to 1 over R. Right? So doubling the resistance means doubling the current. This is not true, so A is wrong. Halving the current. So if you double the resistance, it becomes half the current of what it was. This is correct. The answer is B. There is no change in the current. This is wrong. And depends on the amount of voltage. Here we said for a constant voltage, so this is also meaningless. So the answer should be B rather. Sorry. Okay. Next question. Question 4. A 4-color resistor has the color red, violet, orange, gold. If it is placed across the 12-volt source, the expected current is what? So basically, we go back to Ohm's law. Ohm's law tells us V is equal to Ri. We have the resistance. We could get it through the color code. So we have this one. We also have the voltage, but we don't know what is the current. So current is in fact equals to voltage divided by the resistance. The voltage, we said it is 12 volts. 12 volts. Resistance, we need to find it. Maybe we could remember the color codes for the resistor, or if not, I'm going to provide you the table here. So the first one is red. This band is red, so there should be a 2. The other one is violet. The second band is violet, so there should be a 7 here. The third one is orange. Orange, it should be a multiple of 3. And then we also have the band. But here we don't care about the band because we're asked to find the expected current, which means the average current. So we don't care about the tolerance here. We could forget about the tolerance. We could just look at this. So this would be what? Let's just write it. So this would be 7 times 10 to the 3, which is basically 27 kilo ohm. This is the resistance that we have. So here we simply put 27 kilo ohm, and let's see what we get. So we could take the calculator. We do 12 divided by 27, and this should give us 0.44 milliamp, or the value that we have here. Okay, or which basically is B, right? So this should be 0.44 milliamp. Okay, so it's not A, it's not C. This might be it. You might think this is it, but you could double check your work, and so it's not this. The answer is really B. Let's check if this is what we get. Okay, next question. Question 5. If the current in a 330 ohm resistor is 15 milliamp, the voltage across it is approximately what? Right. So basically we have some circuit. We don't know what it is. It's some circuit. It has a wire. There is some resistor, and then it continues back to this unknown circuit that we have. But we have some information. We know that it has a resistance R of 330 ohms. We know this. So this we know. We know that it has a current that flows in it of 15 milliamp. So this is your current I. The question is, what is the voltage? The voltage across this resistor. This voltage, sorry, this voltage, what is it? So what you do is you simply multiply 330 by 15. So what you could do is you could say 0.33, right? 0.33 kilo ohm times 15 milliamp. And this should give you the answer in volts. Milli and kilo cancels each other. So we take a calculator, we do 0.33 times 15, and that gives us 4.95 volts. 4.95 volts. Here they said approximately which one is it. So here you could basically estimate 4.95 volts to simply 5 volts, right? This is the only option that would work from what we have. So certainly not this, not this, not this, but the answer should be A. So the answer should be A. Let's check. Question 6. A unit of power is the what? So let's go through the process of elimination. Power, is it in units of joule? No, we said joule is a measure for energy, not power. So it's not A. Is power measured in kilowatt hour? This is also not true. Kilowatt hour, we said, is a measure for energy. So this is not true as well, not B. Is it both of the above, A and B? Well, certainly not, so it's not C. Is it none of the above? Yes. So the answer is really D. Let's check. Okay, next question. Question 7. The SI unit, the Système International d'Unité, or the International System of Unit of Energy is which, for energy is which one? So if you want to say energy using the SI unit, would you use volts? No, I mean volts is really for voltage. Would you use watts? That's not for energy, this is for power. Would you use kilowatt hour? Kilowatt hour is a unit for energy, but it's not the SI unit, so it's not D. Would you use joule? Well, joule is in fact an SI unit for energy, and the answer should be C. So next question, question 8. If the voltage in a resistive circuit is doubled, what can we say about the power? So let's see. So we have a resistive circuit. So let's say we have some source and we have a resistor here. And what we want, if we're saying, so this is like some amount V naught, right? And so if the voltage in a resistive circuit is doubled, what can we say about the power? So for this one as is, what can we say about the power for this one? Well, we know from Watt's law that power is equal to V squared divided by R. So this is what we get for this one here, right? So if it's V naught, it's V naught squared divided by R. Now, what if we have another circuit? We have another circuit. This is the original circuit. Now the voltage in a resistor circuit is doubled. So it's 2 V naught. You don't have 1 V naught, but 2 V naught. And again, you have the same resistance, but now the voltage is doubled. Okay? And we ask you, what is the power for this circuit? Well, you can find it. So the power would equal to the voltage that you have, which in this case happens to be 2 V naught squared. Again, this is through Watt's law, divided by the resistance. The resistance stayed the same. And what this equals to 2 squared, that becomes 4 V naught divided by R, V naught squared. V naught squared divided by R, it was this one, the original one. Let's call it P naught. So it's in fact equal to 4 P naught. Okay, so it became 4 times the power of the original one. Okay, this modification made it 4 times that. So what happens to the power? Will it be half? Not true. It's not changed. That's also not true. Does it double? Not true. Quadruples, in other words, it becomes times 4. Yes, this is P naught. This is this power. This is 4 times this one. And we showed it to you here, so the answer is D. Okay, finally, this is the last question that we will solve in this lecture, question 9. The approximate power dissipated by a 330 ohm resistor with a 9 volt across it. So we have some resistor. It is 330 ohms. 330 ohms. The voltage across it is 9 volts. And we want to know what is the approximate power. How much power does this resistor dissipate? So power is equal to V squared divided by R, right? V squared is 9 squared divided by R, which is 330. So now how do we do this? Let's do it. So 9 squared divided by 330, and that gives us a power of 0.245 watt. 0.245 watt. Okay, so the answer is this. So is it 2 watts? Not true. Is it 1 watt? Not true. Is it 0.5 watt? Not true. This is 0.25, so this is approximately 0.25. So the answer should be A.